Hello friends, hope you are all doing well. So today in the video, I thought that instead of taking one specific topic, so if you see my videos so far, I take one particular topic and I make a short video on that particular topic. I thought I will do a different uh, thing today, wherein I'll just present to you some basic aspects of weather dynamics, not talking about one single aspect, but multiple aspects, and mostly from a basic viewpoint, so that this can actually probably lay a platform for people who are interested in weather systems and weather dynamics to take this up as a career, or also to learn more about them and get intrigued. Okay, so that is the idea. So this is going to be a slightly longish video, but given the aspects that we are going to cover, it is not a very long video because, as you will see, different modules will be covered. Maybe this is going to be a 30-minute video, is what I feel. And I just want to put a disclaimer that whatever I am presenting in this video is only the tip of the iceberg as far as the dynamics are concerned. Okay, and there is lot to learn. All right, so let us start. As we all know, the reason we have weather is because the air is restless. It is never in a state of rest. It is always moving, and that is why we have something uh, known as weather. And in all of these, usually whenever we talk about rain or systems, it's always in the atmosphere, right? They always move in the atmosphere, and that's how we get rain. When you talk about clouds, when you talk about cyclones, everything is in the atmosphere. But ocean's importance is seldom underappreciated because the much needed moisture comes from the ocean. Unless and until you have moist air and dry air interacting, you will not have any systems that form. Okay, so role of ocean is very crucial in all of this. So before I get into a little bit of technicalities, let us lay a platform for what are the important directions of motion as far as our system Earth is concerned. So on a rotating frame of reference such as the Earth, which is spherical in shape, you have three important motions which are zonal, which is east to west or west to east, and then you have the meridional, which is north to south or south to north, and you have a vertical direction which is looking up above the ground. Okay, so these are three major directions of motion, and of course the 2 omega that I have shown here is basically the Coriolis effect because the earth is rotating. So for this particular talk or the video, I'll only stick to the northern hemisphere, but similar things happen in the southern hemisphere as well. The reason I'm sticking to northern hemisphere is because you have more landmass in the northern hemisphere, so that's the only reason I'm sticking to northern hemisphere. So on a spatio-temporal scale, if you try to relate the processes that happen in both ocean or atmosphere, then you actually have multiple scales. All right, and this is what makes weather a very complex topic. If you have time scale on the y-axis and the spatial scale on the x-axis, then you have systems that can vary from as small as 1 millimeter or 100 microns, which is as small as the width of your hair, and systems can then go as large as 1,000 kilometer, which is your cases like waves, which are Kelvin waves or Rossby waves, which are like hundreds or thousands of kilometers long. And that is the spatial scale that we are talking about. And the temporal scale is anything, a process that can last for 0.1 second, and a process that can last for thousands, hundreds or thousands of years, like climate change. So this is the spectrum of scales that we have to capture to really pin down weather. And as you know, models don't have this capability because our best capability is 10 kilometers is the spatial resolution, and of the order of 6 hours is how we can on the time scale is the feature that we can capture. So anything which is less than let us say 6 hours, it's very difficult to capture. So that's the reason clouds, which are of the order of 3 hours, are very hard to capture, and their movement is also very hard to capture. Another famous thing quote exists that even if you move your head, wherein your hair is 100 microns, which is just flapping, and that is going to create a turbulence or an eddy in the atmosphere, and that has the capability to change anything in the other part of the world. Let us say you are sitting in India and you are just waving your hand or moving your head. That can change the weather in Africa or America or any place else. So that is why weather is such a complex topic, and one should understand and respect it. And whatever we are able to do with our limited with our limited knowledge and with our limited modeling capabilities, should be appreciated. And of course, we can do better as and when we understand the processes in a better manner. And that's why the importance of dynamics plays a very important role, because until you appreciate the dynamical aspects, then you cannot actually make any improvement in the weather arena. Okay, so as an enthusiast, it's you can follow models, but at the same time you understand what is the which particular spatial feature actually caused that event, and then try to look more into that and try to refine that process and include that process in the model if it doesn't already exist. And that's how you improve your scientific frontier, and that's how you improve your weather prediction capability. All right, so now that enough about why weather is a complex system. But I have tried to explain in a much better manner why it is so. So I hope it gives a clear idea to you now. But now, what happens in terms of convection? So we know that Earth in the so if you look at the tropical region, equator, then it is hot, whereas polar region is cold. So that drives the convection. And very important, without convection, you cannot have these. Without convection, then air wouldn't move; it would be at rest. So this is what causes the restless air, which is the convection. The second thing that actually aids in the restlessness of the air is the momentum. Anything that is moving has a velocity, and anything that has a velocity and a mass will have automatically a momentum. So if you are sitting, you don't have any momentum. As you stand up and start moving, you are a person with some mass, and then if you start moving with velocity v, then you have actually gained a momentum, and that's what pushes you forward or pushes you back. Okay, that's exactly what happens with air also. It attains momentum, and that particular momentum, with the equator it is angular momentum, and as it moves meridionally up, it converts into Coriolis momentum, and that's how the effect of Coriolis also comes into picture. And the third thing is the Coriolis force itself, which is actually the rotation due to the rotation of the Earth. If the air was not rotating, then any parcel will not get deflected. But thanks to the rotation presence, any parcel uh, in the Earth will get deflected to the right in the northern hemisphere and to the left in the southern hemisphere, and this automatically creates a spin, and that's why parcels have automatically a tendency to gain vorticity in rotating frame of system like Earth. And that's why vorticity is always a very important aspect, because vorticity is what causes the rotation, and rotation is what causes convergence, and convergence is what causes the moisture to get updrafted, and as moisture is updrafted, then you automatically form clouds. Okay, so this is where these three things, convection, momentum, and Coriolis, is what governs the bigger aspects of weather. Thanks to all these three things that we just talked about, the convection, the momentum, and the Coriolis, a parcel near the equator will rise up because of the convection. It will move up because of the momentum that it has gained, and then because of Coriolis, it will be deflected to the right, and then it will move down, and this is what you call as a loop. Okay, so that's how you actually attain the westerly winds at the mid latitude and easterly winds near the equatorial region. So this is the Coriolis, momentum, and convection are the reason why you have these east-west kind of trade winds that occur. And the complete picture is this, where you have easterly winds near the equator, and you have westerly winds at the mid-latitude, and that actually causes a formation of a cell which is known as the Hadley cell, and that Hadley cell plays a very important role because it the you have Hadley cell in the northern hemisphere, and you have a Hadley cell in the southern hemisphere. So the point where the two cells meet, that's where the winds also meet from the northern hemisphere, and then from the southern hemisphere the winds meet, and wherever they meet, they create a zone of strong convergence and a low pressure belt, which is what we call as the intertropical convergence zone, ITCZ. And that ITCZ can be seen from any satellite image as a thick, dense mass of thunder clouds, which actually have the tendency to give a lot of rain. And the ITCZ is not stationary, it is moving. It moves meridionally up and down. So it has a southward as well as a northward movement. And that actually is what gives you the monsoon season. So what happens is ITCZ is not stationary. So again, ITCZ formation is very important. The basics is what I have explained. If you take out convection, if you take out momentum, if you take out Coriolis, You will not have Hadley cell formation. If you don't have Hadley cell formation, you will not have ITCZ. So if you want to actually understand the ITCZ movement, then you actually need to look into Hadley cell formation and then how the Hadley cell moves. And if you want to look at the Hadley cell in a more microscopic manner, then you need to understand convection, momentum, and Coriolis. So that's how basics are the building block of weather. Okay, so that is what I'm trying to do in this video or lecture, if you may. So ITCZ actually moves up and down. As you can see, during January, it is very close to the equator. And as you transition to the month of monsoon for India, then you see that ITCZ moves up. So this is now the Hadley cell has been pushed up north. The northern part of Hadley cell is now here. The southern part of Hadley cell is here. And wherever they meet, that's where you have ITCZ, which is the intertropical convergence zone. And this is the belt of low pressure. So strong low pressure exists near the Himalayan subcontinent. And that is what pulls the trade winds from Africa towards India, and that's what gives you the Somali jet, about which I'll talk later. But this movement of ITCZ is very, very crucial for monsoon. As it shifts down in September, October, that's when you get the northeast monsoon. So this movement of ITCZ is very clear during March, April. You can actually look at the satellite images and you can clearly pin down where it is moving. And again, like I said, the ITCZ zone is the very thick, dense cloud, thunderstorm cloud. So you can actually figure out where the ITCZ is lying just by looking at the cloudiness quotient. All right. Now we understand what is the bigger scale synoptic system like the Hadley cell, which aids in the monsoon formation and all those things. Now let us look into some specific terms where we commonly hear these terms in the weather news, which is a cyclonic system has formed, an anticyclone exists over Arabian Sea, a low pressure system has formed, a well-marked low has formed, which will turn into a depression, an offshore trough has formed, a monsoon trough, monsoon circulation. So many terms. So what do these refer to? Okay. So a cyclonic system is nothing but a system which is rotating in the same direction as the rotation of the Earth. Okay. So in the northern hemisphere, if the system is rotating in an anticlockwise direction, so if the winds are in the anticlockwise direction, then you have something known as a cyclonic system. Whereas if the winds are in the clockwise, then you have something known as an anticyclonic system. Okay. So and this is actually this movement of this winds is what causes the low pressure and high pressure systems. So effectively, when the winds are cyclonic, then you have low pressure, and winds are anticyclonic, you have high pressure. Okay. So you can actually find out these low pressure and high pressure systems by looking at the pressure charts or wind charts. So this is a low pressure, and if you look at the wind chart, then it's a low pressure because the winds are cyclonic and winds are anticyclonic, which means winds are clockwise in northern hemisphere. So that is what is the anticyclonic or high pressure zone. Okay, so cyclonic and anticyclonic are basically the broad terms. Like any movement of wind, either clockwise or anticlockwise, is termed as anticyclonic or cyclonic. So if the winds are moving counterclockwise, then it is a cyclonic pattern. If the winds are moving clockwise, then it is anticyclonic pattern. Then you have the next step, which is low pressure and high pressure. That actually comes into picture when the pressure drops drastically to a value at the center. So now the system which is forming gets a little bit more organized. Okay, so the winds can actually be very disorganized in the sense that they would not kind of form this loop, but as they try to form this loop, then you actually call them a low pressure or high pressure systems. Okay, whereas if the winds, so this is not an organized system, but this is still a anticyclonic wind. So it is a anticyclonic motion because the winds are moving in the clockwise direction. Okay, when the winds actually become more organized, then only you give them the name such as low pressure. And when they become even more organized, then you get into depression, well-marked low, depression, and when they are fully organized and have an eye, that's when you call them the cyclone. So why is this important? The movement of the winds, that's what gives you convergence and divergence. So when wind masses converge, then they actually is a low pressure system. So where the air masses move in and they move up, they bring moisture and they lead to formation of clouds. Whereas high pressure systems, they allow winds to come from top to bottom, so thereby cloud formation is not possible. So high pressure is always associated with clear skies, whereas low pressure is always associated with cloudy sky, which is going to give you rain probably. Then you have something known as trough and ridges. Trough and ridges are again wind patterns. Everything is related to wind here. Wind patterns which are not actually forming a closed loop, but they are moving up and down. So this is a trough, this is a ridge, Okay, as the wind is moving from west to east. This is a trough, this is a ridge because wind has dipped down, whereas wind has moved up. So, our other way to talk about trough and ridge is not the dip and upward pattern, but what kind of movement, what kind of pattern they are making. So, this wind is making a cyclonic pattern, right? Because as this wind is moving, if I close this loop, hypothetically speaking, then I will have a cyclonic system because winds are anticlockwise. Whereas when this is moving here, if I close the loop, then it is a clockwise motion, so anticyclonic winds. So the movement of cyclonic and anticyclonic winds, which don't form a loop, is what is called as trough and ridges. So trough is a cyclonic movement of wind, which has the potential to deposit vorticity, okay, because it is moving in the cyclonic direction, and that vorticity is the reason why convergence will happen, and it will lead to formation of clouds. And the other very important thing about trough and ridges is that as the radius of curvature of the trough keeps reducing, then from the conservation of angular momentum, you can see that as radius reduces, the radius of what I'm talking about, if this becomes more uh, sharper, so the peak is more sharper. So you can have two things. You can either have a very long trough or you can have a very sharp trough. So sharp trough are dangerous because they will lead to very strong winds, and strong winds means high vorticity, and high vorticity means more convergence and more dense clouds formation. This pattern of trough is what is very important for offshore trough, is what we call during monsoons, the southwest monsoon system, and that is what gives a lot of rain to the west coast of India. I'll explain that probably in the next slides. So this is basically why systems which are more which have R reduce, when R reduces, why you gain angular momentum is from this classical physics laws where ice skater spins faster when she brings her arms in. So how trough and low helps? They create a situation where convergence can happen, high vorticity deposition, and strong winds will bring in a lot of moisture, and they will lead to updraft forming clouds. So what is the hierarchy? The first thing is trough because you don't have any organized pattern. So winds moving cyclonic form a trough, and then you have low, and then well marked low as things start organizing. So and you have a distinct pressure present at the center. Then you have a low pressure. Then as the pressure keeps dropping, you have the well marked low, depression, deep depression, and then cyclone. So the difference is decreasing pressure and increasing wind. So this has less. This has the as you keep going, the pressure drops and winds also increase, and enhance moisture convergence. Ease of formation. Trough is the easiest to form because you don't need a very organized system. You just need dipping and dipping pattern of winds or cyclonic pattern of winds. So that is easy to form. As you keep going, deep depressions are difficult to form. Pressure again governs the system. So pressure, winds, temperature, moisture, rotation. These are the things that govern the weather. This we have already talked. I just spoke about all of these. And you can actually learn a lot from pressure charts. If you look at a simple pressure chart, you can actually see where are the low pressures, and you actually are on the lookout for the low pressure systems because those are dangerous. And this is typical monsoon season. I think this is in August. You see a lot of low pressure in this region, which is where the ITCZ has moved, because in July, if you remember, I showed uh, the ITCZ location. See, it's near foothills of Himalayas, and that's where a strong low pressure exists, and that low pressure pulls in a lot of winds and moisture, and that's how you get. And this is a trough. You can see a dipping pattern, cyclonic pattern. This is a trough, and that trough gives a lot of rain to west coast of India. So you're on lookout for these kind of systems from pressure charts. What does pressure actually mean? So in very simple terms, high thickness, if the lines are far apart, then it's high pressure. Lines are near, they are low pressure. So you can again clearly see this is a high pressure because lines are far away. And as the lines become closer and closer, it's a high pressure. Okay. Winds provide very good information. I've already talked about this, cyclonic and anticyclonic winds. So I'm not going to dwell more. Typical what you actually do is you put both winds and isobars or pressure on the same chart and you get a lot of information. Okay, just a wrap up of wind charts and pressure charts. So surface level wind help in finding zones of confluence, which is where the winds are meeting and where the updraft will happen. 850 MB pressure charts actually help in checking the sustenance of convergence, whether the convergence will go to higher levels and whether it will result in result in the formation of low pressure or a trough and ridge kind of a pattern. Then 700 millibar level is helpful in finding circulation patterns, which are either low level circulation or upper level circulation, and also low pressure areas. 500 millibar is very, very important because it will help in finding the regions of vorticity and associated instability. So if you are interested in finding deposition of vorticity, then 500 millibar level is the most important to check. 300 millibar is very important during winter time, where you actually look for jet stream and polar vortex kind of systems. And when a cyclone has formed, you actually look at the 300 millibar level for upper level ridges, or ridges are high pressure zones. So because the cyclone tends to take the move along the ridges. So these are the importance of the wind charts at different levels. And again, when I say wind, I don't only look at wind, I also look at pressure, because those two go hand in hand. The next important aspect when you talk about weather is waves, because the waves is the one that actually carry energy from one place to the other, and they transfer energy from one place to the other, resulting in lot of energy transfer. How they affect is you have major modes of variability, like ENSO, which are very long, El Nino, which are very long scale variability. Then you have the meridionally oscillation, and all of these actually result in formation of clouds, but they result in formation of clouds through a very important mechanism, which is waves, which is like the middleman. So if you take out waves, then their interaction will not be there. So the connecting point between any of these big structures and cloud is the waves, because they have to transfer energy. The waves come in many different, can be characterized as dispersive or non-dispersive. Dispersive is basically, you have, when you talk about waves, you have phase speed and a group speed. Phase speed is just the velocity at which the wave is moving. Group speed is the transfer of energy. Okay, so if the wave is moving and the group velocity and the phase velocity are the same, then what it means is that the energy is transferred in the same direction as the wave. However, if the phase velocity is negative of group velocity, then you see the wave is moving in one direction, whereas the energy will move. So blue is the energy transfer. So although the wave is moving in from left to right, energy is being transferred from right to left. And you can have other different aspects. A dispersive wave is when the phase velocity and group velocity are not the same. This is a this is a non-dispersive wave. When both are same, then it is non-dispersive. So you have different types of waves which are moving from west to east or east to west, and that movement alone is not important, because, like I said, if they are dispersive, so even though a Rossby wave moves from east to west, but its energy will be always to the back of it, like it will always give energy in the eastward direction, because they are dispersive waves. Rossby, equatorial Rossby wave or MRG wave. So even though their direction of movement will be from east to west, but the energy transfer will happen in the other direction. That's why it's very important to understand these waves patterns and how they transfer energy, because otherwise you will actually get everything wrong in terms of weather dynamics. Okay, so you can put a map and you can see Kelvin wave is a non-dispersive wave. Kelvin wave is something which moves from east to west to east. They are always moving from west to east, and they're non-dispersive. That means they will transfer energy also in that same direction. And then you have MJO, which is again a east to west wave, and it is again a non-dispersive kind of a wave. So energy will always again be transferred in the same direction as the wave is moving. I can talk about two important waves, which are Kelvin and Rossby waves. Kelvin wave, it's not dispersive, so if you see the amplitude has not changed. Okay, so energy transfer will happen in the same direction. Whereas Rossby waves are very tricky, because they start with small waves and then they actually gain amplitude, and that actually results in a lot of trickiness. That leads to a lot of tricky feature, because as the amplitude increases, they can break down, and they can transfer energy in a very random manner. That's why that's why Rossby waves are very tricky. Let me skip this slide, not needed. You can look for these Rossby and Kelvin wave signatures through the movement, whether the propagation. So westward propagation means Rossby wave, eastward propagation means Kelvin wave, and also the frequency. So Rossby waves have a very high frequency of 10 to 14 days, whereas Kelvin waves are slightly shorter, 7 to 14 days. Long wave, there are also long frequency Rossby wave which happen during monsoon seasons. Those have a lifespan of 1 to 2 months, so they can linger around or move as a pattern of wave for almost 1 month or 2 months. And these usually very long frequency Rossby waves are seen in ocean, in the ocean. Okay, in the atmosphere you usually have a very short frequency Rossby waves. You can also see the waves from the Hofmover diagram, which is the diagram of longitude versus the time. and different waves propagation. So you can find when that wave reached the which part of the continent, whether it was in Indian Ocean or the Pacific Ocean, and those kind of things. And then you have these waves, eddies, and vortices. So, like I said, anything which is a mass of air, as these waves starts to, so take Crosby wave, the waves, this same picture, the wave started very small and then it went amplified, right? So same thing happens. So the wave started like a very small, high wavelength wave, and then it started undulating, and then as it undulated, it started splitting. As it split, it became a trough and a ridge, which means a cyclonic and anticyclonic system. Cyclonic system then pinched off as a low pressure, and anticyclonic system stayed as a high pressure, and this low pressure moves down. So that this is how the cold polar air during winter time is dropped to lower latitudes, and that is known as the meandering of jet streams, and that is how you actually have either systems forming, extratropical systems forming like western disturbances, or you have in atmosphere. I'm talking about cyclones are different because they require ocean as well. This is purely in atmosphere. So or you have these polar vortices that drop down and come down to low latitudes, giving a lot of snowstorm, like extreme snowstorms. So the pinching of polar vortices are very common. And this is where I want to put a disclaimer that both vortex and trough mean a low pressure region, but a vortex is a much smaller zone compared to a trough. It is much more localized, and it is a stronger zone of flow, and it is associated with very heavy precipitation for a relatively short duration of time. So it can dump, a vortex can dump 100-150 mm of rain in a period of 3 hours, whereas a trough will give you much more widespread heavy precipitation for a longer period of time, wherein you will get 100 mm or 150 mm in like 7 or 8 hours. That's why vortex is very tricky. Okay. All right, so that brings me back to the last model, which is the southwest monsoon. Like I said, the southwest monsoon is governed by many factors, which one is the differential heating of land and ocean. Then you have the Tibetan Plateau, which actually heats up, pulls the ITCZ up. So that ITCZ, which is the intertropical convergence zone, settles near near the Himalayan region. And along with that, you also have something known as a monsoon circulation, and these two put together is what they call monsoon trough. And then you have Mascaron High, which is the high pressure in the southern Indian Ocean, which actually deflects the winds, and then that's how you actually have the Somali jet formation, which brings a lot of moisture to the central part and western parts of India, and actually it brings a lot of moisture throughout the Indian subcontinent. So I'll take a minute to explain what is this monsoon trough, because it's a very tricky term. So monsoon trough. So you have ITCZ during normal time, but during monsoon, what you have is you have ITCZ, which is this line, plus you have a cyclone. You have a cyclonic circulation which is very active, and that is what is known as the monsoon trough. Monsoon trough embeds both the ITCZ and the circulation, which is cyclonic circulation. And how does that cyclonic circulation come into picture? That cyclonic circulation actually comes into picture because of the west-east movement of winds. So you have the westerly winds which are moving from the Arabian Sea, and then above that you have these easterly winds because the Hadley cell has moved up. So you have these easterly winds. So if you see it, if you look at this, it automatically forms a cyclonic circulation, right? So east motion and west motion, east motion, west motion. So it automatically forms a cyclonic circulation of winds, which is known as the monsoon circulation. So the monsoon circulation plus the trough put together is known as the monsoon circulation plus the ITCZ is what is known as the monsoon trough. So this again just tells you that entire thing. ITCZ moving up, cross equatorial flow brings the Somali jet, and that Somali jet brings westerly winds. And above this ITCZ line, you have the easterly winds, and wherever the two winds meet, you have an active cyclonic circulation of monsoon, and that active cyclonic circulation of monsoon is what creates. So you have this cyclonic wind pattern, which creates this monsoon circulation, and that is what that is what keeps the monsoon alive for almost 3 months. And the role of Hadley cell is also highlighted here, because unless and until the Hadley cell moves to the north, you don't have the ITCZ shifting up. So this is the circulation that I was talking about. This is so you have the westerly winds and you have the easterly winds. So as they keep moving, you have this cyclonic circulation that creates in the northern hemisphere, and that plus ITCZ is what is known as the monsoon trough. The circulation is very important because it keeps the vorticity deposition alive. So Unless and until you have this cyclonic circulation, you cannot have this vorticity that gets deposited. And the second thing is you will not have any systems forming either in Bay of Bengal or Arabian Sea. The reason the cyclonic circulation ensures that during monsoon season you have at least 10 to 14 good systems forming, which will move along the axis of monsoon trough, and they will dump lot of rain. And that's why southwest monsoon season you almost have like 889 mm of rainfall throughout the country, which is massive. So these are the specific features. And during the northeast monsoon, ITCZ shifts down. The cyclonic circulation, cyclonic circulation also shifts down, only active in the southern part of India. And that is, as the southwest monsoon transitions to northeast monsoon, the cyclonic circulation systems become weak, and that's why northeast monsoon doesn't give as bountiful rain as southwest monsoon. Okay. So, like I said, this is the offshore trough. The offshore trough is the dipping pattern of winds or the cyclonic movement of winds as the winds approach the western part of India. As they approach the western part of India, they deposit a lot of cyclonic vorticity in this region, and the strong westerly winds from Arabian Sea, they push these. So there is a cloud band formation along this line, and the strong westerlies actually push these cloud bands towards the western parts of India, triggering heavy to very heavy or extremely heavy rainfall episodes. And then any system that forms in Bay of Bengal will move. This is the monsoon trough. So this is offshore trough, which is different. This is the monsoon trough, which embeds the ITCZ plus the monsoon circulation. So any system that forms in Bay of Bengal will actually move along the line of ITCZ, and this along the line of monsoon trough. And this monsoon trough is not stationary; it moves up and down. So it moves. Sometimes it is south, sometimes it is north. When it moves to south, then Kerala gets very heavy rainfall, floods-like situation. When it is in this region, in the central part of India, that's when Mumbai gets flooding type of rains, including Gujarat, and also parts of Madhya Maharashtra and sometimes even Hyderabad, Telangana places as well. And when it moves north, then Uttar Pradesh and Northeast India and Nepal, all these places get a lot of floods. So this movement of monsoon trough is very important feature of monsoon, and lot can be said by just by tracking this monsoon trough. And it is always slanted; it is never straight. The reason it is slanted is because of the effect of Coriolis force. So this monsoon trough, which is also known as monsoon intra-season oscillation, can actually be found through models. There is an active IITM model, Indian Institute of Tropical Meteorology, which tracks the MISO, how it moves, how the monsoon trough moves during the monsoon season, up and down, north and south. Okay, I mean, a lot of things can be actually known, but this is just a guideline. It doesn't. There are a lot of issues associated with exactly tracking the monsoon trough, but still, it is some guidance. This is that monsoon circulation cell that I was talking about. You can clearly see a distinct circulation cell, which is covering entire India and giving widespread rain. This is the monsoon trough axis. Monsoon trough axis is where the westerly winds and the easterly winds meet. So this is the westerly motion. This is the easterly motion. So wherever they meet, that's where the monsoon trough forms. And this system, which has formed in Bay of Bengal, will actually move along the monsoon trough axis all the way from Bay of Bengal to western Rajasthan, dumping a lot of rain, mostly below the axis of monsoon trough. Alright, so this is bringing me to the last slide, which is my final thought. Low pressure is the starting point for inclement weather. So hierarchy and all these low pressure actually start from the wind movement and the pressure, how the pressure behaves, wind and pressure. Moisture is automatically coming from the ocean, no problems there. But low pressure is the starting point, and you have different offshoots of low pressure like trough, you have vortex, you have well-marked low and everything. But low pressure or cyclonic system is something which is the starting point. Cyclonic system is a very broad term. Low is a specific term, trough is a specific term, well-marked low is specific terms. ITCZ and monsoon trough are dynamically different because monsoon trough actually embeds ITCZ and the monsoon circulation, distinct monsoon circulation cell. Circulation means a well-defined structure. Pressure and wind chart actually tell a lot of information about weather and its dynamics, and temperature is important, but pressure and wind charts are the ones which actually have a lot of host of information. And these are actually important for moisture convergence. We always look at we always look at the output, but I feel like we should always take one step back, and instead of saying that moisture has converged, we should actually see why that moisture has converged at that location. And that actually can only come out from dynamics, which is looking at wind charts, pressure charts, and looking at basics of convection, momentum, and this Coriolis force and all these things that I talked about. So everything, I mean, a lot of details is in the basics. So that's why I thought I will make this video. And those who are interested can take up a lot of things from this video. And of course, this is not the only video which is available. There's a lot of information available over internet. There are a lot of books, a lot of other nice videos which are available. So you're free to look at any of them. But I just wanted to make this video to give you the basics of weather dynamics. Okay, that which is of interest to me. Okay. So thank you so much for watching this video, and please subscribe to this channel. I know it is a long video, but I hope it is worth it. I had always wanted to make this video, and I'm glad that I could make it today. Please share it, and I hope you learned something about weather by watching this video. In the end, if you would like to get more information, then there is actually a course that is being offered in IIT Bombay. If you go to cep.iitb.ac.in and click on courses, sorry, if you go there, click on course calendar, click on courses. Then there is this basics of weather dynamics, which is being offered in December, 19th and 20th of December. It's an online course, 6 hours per day course, and it is it's not opening up, but yeah, if you open that, then you will see that it is a 2-day course on 19th and 20th of December, which will talk a little bit more about whatever we discussed, more aspects of monsoon, more aspects of El Nino, La Nina, and all those things. And many things will be discussed. So if you're interested, you can sign up for this course. There is a small fee associated with it, so you can take a look at it. All right, thank you again, and I will sign off now. Have a great day.